Hello students and welcome to another video. I'm your teacher Mr. Flynn, and today we're going to be talking about covalent bonds. Now this is probably the most challenging section. Before we talked about ionic bonds and metallic bonds, and these are the more simple of the two, because ionic bonds are just electrons are being exchanged, or not exchanged, but just being stolen or taken from one element to another. Metallic bonds, the electrons are just free-flowing in between all of the cations. Okay, now in covalent bonds, they are being shared with each other. So they share electrons to achieve a full octet. So for example, right here, we have fluorine. We have two fluorines, and they both need one electron. So in order to get that full octet, they will then share electrons with each other. Okay, and we don't draw it like this right there as two dots. We prefer to draw it as a line in between those two. So each line that you see is representing two electrons. So and this is an easy example where this needs one electron, this one needs one electron. Well, what if we just share the one electron that we each have, and so we just connect that dot there, okay? And our goal here is to achieve a full octet, all right? And you'll notice that a lot of these atoms that are doing covalent bonding are all nonmetals, okay? Because they're takers. Remember that. They are takers. And takers would rather share with each other because they can't fully take an electron from another taker. So they have to share and work together to share those electrons. So here again, we have hydrogen. Now, hydrogen has, to get a full octet, it only needs two electrons in that octet. All right, so it's more of a duet because it's the only example where you only need two electrons. Because if you notice on the periodic table, there is no p block for level 1, right? So for example, if I look here on my example at the very beginning, oh, let me back up here. That wasn't very good. Right here, see how there's only two electrons in that first energy level, and then in the second energy level, there's 8. All right, so for hydrogen to have a full octet, it only has one ring. So whatever goes in here, there's only needs 2. All right, but hydrogen only has one electron, so it needs to have another electron to pair with to have a full octet. And so what we're going to do is just have these two electrons here share, and they're going to form a bond like that. All right, and then down below we have oxygen. Okay, and it needs 2 electrons, and then hydrogen needs an electron. So these hydrogens will pair up right here with this oxygen right there, and then form bonds like this. Now, some kids can get this confused because if you draw it like this, all right, that could also work, right? Because you got 1, 2, 3, 4, 5, 6, 7, 8. So oxygen has 8 electrons, hydrogen has 2, and hydrogen has 2. So why do we draw it this way instead of that way? Well, the reason is because of geometry. These electrons here on the top of this hydrogen are huge, and they take up a lot of space, and they're pushing on everything. All right, so if we do it like this, actually let me back up here. I'll erase a part of this drawing to make it easier to see. These bonds are huge, and they put pressure on these bonds. Now, if you look here, these electron pairs are squishing my hydrogens, the bonding that's going on inside these hydrogens. So it's not set up in a way where it's giving it flexibility, all right? So these hydrogens, three-dimensionally, are going to move around, and they're going to look more like this, and they're going to be on top, and when they push down, it gives flexibility for these hydrogens to move a little bit, all right? So there's certain configurations in which how they form, and we'll talk about that when we get to Vesper theory. The shape that oxygen has, oops, not that one, it's right here, it's called bent, because it's bending those bonds down below here. Okay, all right, let me clear this up a little bit. Drawing too much on here. okay? Now, these are single covalent bonds, okay? So if you see here, these all have 1, 1, and 1. And then we can have double covalent bonds. So if I've got an electron here, maybe they can share, and then I'll use a different color. Let's use green. We have another electron, maybe they share. So now we've got a double bond. And so they both need 2, so why don't they just share that lone electron so that they can both have a full octet? And that's what these orange circles are doing, is showing you that they have a full octet. That's how you know you've got it balanced, all right? Because you want each element to have a full octet. Okay, here's another example of carbon dioxide. So oxygen needs 2, and then carbon needs 1, 2, 3, 4. All right, so whenever you're doing these problems, you always start with the one that can make the most bonds. So which one can make the most? Is it oxygen or carbon? Well, looking at my example, carbon can make 4 bonds, so we're going to put it in the middle. And then once it's in the middle, you can start dishing out who needs what. So if this oxygen pairs with this one, and then this oxygen is going to pair with the other side, and then now you get something that looks like this. All right? You just got to start pairing them up to see how they fit. But always start with the one that can make the most bonds. That's what we're looking for, okay? Clear this up a little bit. All right, now triple bonds is the same thing as our covalent bonds here, our double covalent bonds, in the sense that each element is sharing more than 1 electron. So this one has 1, 2, 3, and this one has 1, 2, 3. So why don't these all just pair up together and make a triple bond? And this triple bond is really strong, by the way. It is strong. All right, because there's 3 of them holding it together. Okay, it took a long time to figure out how to break that bond, and it took intense pressure and heat to break those bonds. And once we were able to do that, we really create fertilizers, and we could grow more crops and increase our population. Okay. Now, down below, there's some rare exceptions to this, and that is between carbon and oxygen. So if we look here, carbon wants to make 1, 2, 3, 4 bonds, and oxygen wants to make 2. So this one will bond with this one will bond with that one, and then the problem is right here that we have 1, 2, 3, 4, 5, 6 electrons for carbon. Ooh, carbon only has 6 electrons. Oxygen has 1, 2, 3, 4, 5, 6, 7, 8. And so oxygen is okay, but carbon is not okay. All right, it only has 6. So this lone pair, we call these lone pairs because there's 2 of them, these 2 electrons, it's going to move down and form a bond with carbon. So now carbon has 8 and oxygen has 8 electrons. Okay, this is the only time I'll show you this example. I'm not going to expect you to draw this on a test, but I want to show you that there is just a little more complexity than just simply connecting dots. Okay, there's a little bit more going on than that. Okay, I wanted to show you an example where some of the rules get bent. But most of the examples I will show you will look like this between nitrogen. Okay. Now, down below, we have electronegativity. Okay, and this is how much an atom wants to gain electrons. And so remember we talked about in the past how we have our peasants and our nobles. So right here we have our nobles. They do not want electrons. They already have a full octet. But everybody over here, okay, needs to, actually let's use a different color. Let's use red again. Everything over here on this side of the table needs to make changes. So everything up here in this top corner, okay, it wants to take, right? And everything over here wants to give. And so what we're doing between that staircase, between metals and nonmetals, we're kind of classifying them as givers and takers. And we've talked about this. But the ones that want to take the most are the ones that work up to this corner here. So fluorine is going to be the most electronegative. So it's going to want to steal electrons the most. Okay, that's basically the premise of electronegativity. And we actually have a chart down below that represents this, and it's called the electronegativity reference. And this is a value system where it talks about the likelihood of electrons being taken and stolen from each other. You need to fill this out. So pause the screen and then fill this out. All right. Each of these elements, okay, this is the S block and this is the P block. All right, and there's elements in here, and we have a value associated with it. And if you notice, helium all the way down to xenon, we're just going to write a 0, okay? And it's going to be in purple. Please color code this. It's easier to read when it's color coded. So purple means it doesn't want to react at all. It doesn't want to do anything. Red, okay, it badly wants to take electrons. So oxygen and fluorine are going to be hungry for electrons, and they want to steal them. Okay, orange is kind of intermediate. All right, these ones right here, they are not as badly wanting electrons as oxygen and fluorine. Okay, the green ones are becoming more like neutral, where they like want to take electrons if they can, but they'd rather just give or share electrons. And then over here in blue, these want to give electrons, okay? And so what we're doing is we're kind of color coding this to show you that as we work our way up to this corner, they are becoming more and more electronegative, okay? 4 being the highest value and the lowest value being 0.8. So rubidium is not going to be stealing electrons, okay? Fluorine is. All right. It'd rather give away its 1 electron than to take electrons. All right. Now, we have trends for this, and we talk about being at nonpolar, polar, and ionic, and I will come back to this and talk about it with you. But for right now, I just want you to write out this reference sheet here, and let me just clear this out. All right. And then let's go back up here and talk some more, okay? Now, we've just talked briefly about how electrons share how atoms share electrons. I'm trying to erase this and talk at the same time, and I can't do it. Now, there are multiple ways in which atoms can share, all right? Think of it like this. I have a twin brother, and sometimes my parents would come home with, let's just say, a brownie. I'll use this space right here. We have a brownie. Now, if me and my brother are in the room together and my parents bring home this brownie from like whatever social event they went to, and they're like, oh, we'll feed it to the kids, you know, and we would be there together, we would split it as evenly as possible, because there's a rule in life, and it goes like this. It goes, you split, I pick. So if my brother splits the brownie, I get to pick which one I want. Because if I split it unevenly, he'll take the bigger one, because we're both boys and we like to eat food, right? So are we sharing equally? Yes, we are. So we are both sharing equal amounts. Now, what happens if I get there first? And it's a brownie, it's a square or a rectangle, and I say, well, he's not here, so I'm just going to help myself, and I'm going to take the big piece, and then he can have the smaller piece. And he won't know the difference, right? So is that sharing? Oh, yes, it's sharing, but it's not sharing equally. So if you share equally, there's a term for that, and it's nonpolar. And if you're sharing unequally, it's called polar. Okay, those are our terms. Now, could I come in and just take the brownie in whole like this? Like I just eat the whole thing to myself and he doesn't know, because if he doesn't know, it doesn't hurt him, right? Well, we call that fully stealing, and we talk about that as an ionic bond, and that's up here. All right, ionic bonds are stealing. This chlorine isn't even giving sodium a chance. It's like, I'll just help myself. I'll take that electron from you. We're not going to share at all. All right, so there's 3 types of sharing. So nonpolar, let me back up here. Oh. Okay, they are sharing equally. And polar covalent bonds, they are not sharing equally. All right, we just need to emphasize those 2 points. Now, when we share electrons equally, all right, what's happening is that we are calculating this with our values down below. So remember this electronegativity reference? You're going to be using this to calculate polarity. So in this example, okay, sharing electrons, we have oxygen and oxygen. So oxygen's value is 3.5 minus 3.5 gives me a value of 0. And anything between 0 and 0.4 is nonpolar. So if this is 0, it's definitely falling into the nonpolar camp. And there's like a range of values that we can have. And let's look at another example, and then it'll make more sense. So let's look at water. Okay, the reason why water is polar and the reason why water likes to interact with the world is because it has charges associated with it. So here in oxygen, we have a 3.5 minus 2.1. So 3.5 minus 2.1, the difference is 1.4. That definitely does not fall into the 0 to 0.4 range. So we have a new range. So anything between 0.4 to 2.0 is polar, and 1.4 falls right in the middle of that. So this means that they're not sharing equally. So anytime there's a bond here, we can calculate how they're being shared. And we draw this using a dipole. So this right here is called a dipole. So we have a positive end pointing to the negative end. So it's like pointing to negativity. You can see the positive end right here, right? And it's pointing toward negative. And there's a special little character. We draw it like this, okay? That special character means partially. So it's not fully negative, fully positive. It's just partially positive because the electrons, I'll draw back it up here a little bit, clear this out. Okay, the electrons are just near this oxygen more. So if I have this example here, just like right here, all right, this bond, what it really looks like in the world is it looks like this. The electrons are much closer to the oxygen than the hydrogen. They're hogging that negativity. So it's going to be partially negative on one end and then partially positive down here because the oxygen is taking those electrons. All right, and we draw that using a dipole. Now, if it's fully charged, we're looking at ionic bonds. You don't see here on the chlorine and sodium that it says partially negative. That doesn't exist because it took the full electron. It stole it. Down here, they are not stealing the electrons. They are sharing them, but they're sharing them unevenly. They're a lot closer to that oxygen than they are to the hydrogen, okay? All right. Hopefully you're starting to pick up on this. If you need me to help talk to you some more, I can. But the idea is polar is not equally, and sharing electrons equally is nonpolar. Okay. Now, if I come to the bottom down here, there's a reference sheet, and I would like you to put this into that reference sheet. And this is the trends. Okay. If it's between 0 to 0.4, if we do the difference, if we subtract them, if it's between 0 and 0.4, it's nonpolar. If it's between 0.4 and 2, it's polar. And if it's over 2, it's ionic. But there is an exception, and there is a gray area. Okay, there is this area between 1.6 to 2.0. If it falls in this range, okay, let's say it's 1.8. Well, you have to now look at the combination of the elements. So if a combination is two nonmetals, it is definitely polar. Okay. Nonmetals share. If it's a combination of a metal and a nonmetal, it's ionic because the nonmetal is going to take the electron from it. All right? Nonmetals share, metals and nonmetals take from each other. Okay? There are several examples. All right, I think it's between like magnesium and oxygen. Let me look here. I think magnesium and oxygen is an example of it. Let me look this up real quick. Hold on, which one was my example that I used before? That won't work. Oh, I think it was magnesium and chlorine. That's what it was. So if I have magnesium and I have it bonded to chlorine, so magnesium is 1.2 and chlorine is 3.0. So 3.0 minus 1.2 gives me a total of 1.8. Okay, so if what's 1.8, according to this scale, it is polar. But it's not polar because we have a metal and a nonmetal. If it's a metal and a nonmetal, we know it's ionic without doing any calculations. All right. If we have two nonmetals together, then we have to figure out how is it sharing? Is it sharing equally or not equally? Okay. So just pay attention to that as you go through this, that you understand that metals and nonmetals make ionic bonds and two nonmetals make covalent bonds, but you have to differentiate if they're polar or not polar. Okay. You have to do that for nonmetals. Okay. All right. And then the last piece to this, I have a lot of stuff on here. There's a lot of lines on here. I'm trying to clear this out. is Vesper theory. Okay, so this is only nonmetals. Okay, this does not include ionic bonds because ionic bonds just take electrons from each other. They're now charged and they're just attracted to each other. But if they are nonmetals sharing electrons, okay, they can form shapes. So if they're forming a shape that's in a line, we call it linear. Okay, and this is 0 lone pairs. This kind of got moved on me. This is the title of this box. So we have 0 lone pairs, 1 lone pair, and 2 lone pairs. All right, it's kind of categorizing them. So if it has 0 lone pairs, we have a central atom. Okay, it could be like carbon bonding with an oxygen like this. All right, we would call that linear. All right, another example could be like carbon bonding with oxygen going like this. Oh, not oxygen, sorry, my bad. These will be like chlorines down here like this. All right, and this will form a shape like trigonal planar. That's what we call it. So it's a triangle, trigonal, and it's planar, meaning that if you were to rotate it and look at it from the side direction, it would look flat. So it's like a flat triangle. That's kind of how I would look at it. And you're going to be able to look at these models. I'll have some in class for you. And then tetrahedral, okay, is like carbon bonding with hydrogens here. Here's another example. Okay, this is methane. In a three-dimensional space, this one's going back into the page. This one's coming at you, okay? All right, so it's three-dimensional. And I'll show you an example of this in class, all right? All right, so it's got 4 of them. So tetrahedral is that one. And then bent, there's 2 bent ones. And it depends if you have 1 or 2 lone pairs. So if you have 1 lone pair, these lone pairs take up a lot of space, and they're bending our molecules, okay? And then we have at the very bottom, ooh, this one got taken off. Let me put this on here. This one is pyramidal. All right. So a pyramidal looks like a pyramid, and it's got 1 lone pair and then 3 below it. This could be something like, an example of this could be like nitrogen bonding with a bunch of hydrogens here. All right, here's an example of that. Also known as ammonia. And this nitrogen is being bent, the hydrogens are being bent by this lone pair, and it's forming a pyramid shape. And I can show you what these look like in 3 dimensions in class, but you just need to be familiar with these terms and the shapes going on with these non-polar covalently bonded molecules. Okay, that's what's going on. So to classify those. And like I said earlier, Na and Cl do not form shapes. Na is positive, chlorine is negative, and they're attracted to each other because of their charges, not because of their bond angles. This is not linear. Okay, a lot of students mix this up. It's not linear. Okay, linear, carbon and oxygen are sharing electrons. They are covalent. Okay, all right. There was a lot in this video, so I may break this into 2 days. I'll see. But as far as like this material goes, please come back and review this and go watch my review videos at the bottom of the resources. I show you more examples and I talk through it with the book. Okay. Thanks again for watching.